What a surprise! SpaceX revealed the real reason why Starship's heat shield turned orange during re-entry. It turns out, this wasn't a technical failure at all, but the result of a special experimental metal plate the company had installed, which unexpectedly triggered a chemical reaction. So, how did this happen, and what does it mean for the future of Starship's metallic heat shield? Let's find out in today's episode of Alpha Tech. Many might not realize this, but Flight 10 was one of those rare occasions where we got to witness Starship touching down gently on the ocean, a truly thrilling and exciting moment. Clearly, this is also a major achievement, proving that ship version 2 is far from being a flawed design. For many, it may have looked like just another landing, but from an engineer's perspective, pulling it off requires an extraordinary level of fine-tuning and precision. From mission control, precise commands are sent to the ship via Starship's RF system, with extremely low latency, just a few hundred milliseconds. Inside, the guidance software integrates data from GPS, INMU, and altimeters through the internal data bus, then reignites the Raptor engines at the exact moment needed. The thrust has to be adjusted in real time, synchronized with the COPV system to maintain proper fuel flow pressure. All of this happens autonomously within seconds, making that smooth splashdown we see on video the result of an incredibly complex, finely tuned system. And that's something most people don't really notice. In fact, 99% of viewers were more focused on that strange orange patch on Starship's heat shield just before splashdown. Scroll through any forum or social media page, and you'll see endless debates about this orange mystery. To clear up any guesswork, Elon Musk explained it himself. The orange color is rust from rapid oxidation of metallic test tiles. That makes it pretty clear. Before the flight, they had installed a metallic heat shield tile on the ship's body, alongside the traditional ceramic thermal protection system. These tiles were added to evaluate their performance compared to regular ceramic tiles, and also to see if it could meet the demands of rapid reuse. They were placed right where the orange oxidation streaks started to flow. But why does that metal tile create such a big orange streak? Let me explain. From a physics perspective, metals, especially steel or iron alloys, tend to oxidize when exposed to the open air without any protection. However, in space, particularly in the vacuum of deep space, there are almost no oxygen molecules or water vapor for the metal to react with. The situation changes dramatically during re-entry to Earth. Around 110 kilometers altitude, UV radiation from the sun breaks apart oxygen molecules, producing highly reactive atomic oxygen. As Elon said, metal oxidizes fast at Mach 25. This causes the metal tiles that SpaceX installed on Starship to oxidize thousands of times faster when exposed to the high temperatures and plasma during re-entry. You could see the plasma around Ship 37 turning pink at about 94 kilometers altitude, and it kept intensifying, making the vehicle glow with ionized gas. That extreme heat alone would erode the metal surface, releasing tiny iron particles. But what really spread those particles was the activation of the active cooling system. As the cooling liquid escaped through microscopic holes, it carried the oxidized iron outward, leaving behind a thin layer of rust-colored residue. Without those experimental tiles and their liquid cooling, the heat shield would have stayed much cleaner and mostly black. But with them, the surface ended up coated in this orange iron oxide powder. These particles then settle on the surrounding ceramic tiles, and when the ship encounters humid air or seawater after splashdown, they spread and react further, forming the orange rust streaks. The location of the streaks usually matches where the metallic test tiles were installed, starting from the lower nose cone and extending downward. Honestly, seeing Starship glowing orange like that instantly reminded me of NASA's SLS vehicle. But the sad truth is, SLS can only launch and then get thrown away mid-flight. It will never pull off a smooth landing like Starship and Super Heavy. Yes, that means Starship's ceramic heat shield system is still working well. It can be studied and improved for even greater durability in the future. But did you notice? Around the nose cone area, it also turned white, didn't it? As Musk said, worth noting that the heat shield tiles almost entirely stayed attached, so the latest upgrades are looking good. The red color is from some metallic test tiles that oxidized, and the white is from insulation of areas where we deliberately remove tiles. The truth is, SpaceX intentionally removed a few ceramic heat shield tiles in those areas to expose the insulation underneath. This insulation, usually made of composites or heat-resistant fibers, can handle extreme reentry temperatures. And because these materials are typically white, they help reflect heat and reduce thermal transfer to Starship's stainless steel skin. During reentry, Ship 37 faced the extreme temperatures we just discussed. In areas without the ceramic tiles, the white insulation had to endure direct heat, causing it to melt slightly and spread around the nose cone as it interacted with the atmosphere. Unlike the metallic test tiles, which oxidized rapidly due to atomic oxygen at around 110 kilometers altitude and created orange iron oxide streaks, the insulation contains no easily oxidized metals. That's why it stays white instead of turning orange. So after this test, is Elon Musk still planning to use metallic heat shield tiles? Well, SpaceX hasn't released the full results yet. Beyond the obvious signs of oxidation, we still don't know if there are deeper structural issues, like warping or even melting under extreme temperatures. But what we do know is this: even the oxidation itself already gives us some important insights. First, metallic tiles will inevitably oxidize after each flight. With just 3 test tiles, we saw a huge portion of Starship stained orange. Imagine what thousands of them would look like. If left untreated, this could slowly degrade the surface. Of course, the erosion itself may not be severe, but SpaceX would need to wash off the oxidation layer after every flight. While that's not too labor-intensive, it doesn't exactly fit the vision of rapid 24-hour turnaround. Second, metallic tiles are designed for multiple reuses, without needing massive replacements like ceramic. Flight 10 already proved this. Starship survived with deliberately removed tiles, plus the metallic test tiles, showing that the system can withstand worst-case scenarios and still be reused. If optimized, metallic tiles could help Starship truly become fully and rapidly reusable, far beyond the space shuttle, which required months of inspection after each mission. Third, SpaceX doesn't see oxidation as a deal-breaker. They treat it as valuable data for optimization. In the future, they might test superalloys like Inconel 718 or Hastelloy X, which naturally form protective oxide layers. These materials can withstand 1,200 to 1,500 degrees Celsius, while their oxidation rates are dozens of times lower than standard stainless steel. In short, even if SpaceX has to clean off oxidation after every flight, Starship's reusability goal remains achievable. And if ceramic tiles continue to perform reliably without catastrophic failures, their lighter weight might still give them the edge. So here's the big question: can metallic heat shields truly replace ceramic tiles in the future? Share your thoughts in the comments below. When Musk first proposed the idea of a metallic heat shield, he admitted that integrating a regenerative cooling system would be a major challenge in making it work for Starship. The concept is to use tiny holes and pump liquid water, or even propellant, through them to actively cool the surface. But here's the catch: this has never been seriously proposed or tested before. While the general idea has been around for 50 to even 100 years, there has never been any significant research into metallic heat shields that rely on transpiration or film cooling. In fact, metal-based thermal protection systems are already rare, and they remain largely untested in modern aerospace. Still, there is a potential solution, and that's the approach SpaceX applied in Flight 10. Back in the 2010s, Germany's aerospace agency, DLR, experimented with a material called Proxelit 170, a porous thermal protection material made of 91% aluminum oxide and 9% silicon oxide. In wind tunnel tests, they were able to cool P170 from a blistering 1,750 degrees Celsius, or 3,200 degrees Fahrenheit, down to just 25 degrees Celsius using water. The cooling rate was about 0.065 kilograms of water per second for every square meter, under a heat flux of 200 kilowatts per square meter. For Starship's stainless steel design, though, things look very different. Stainless steel can tolerate much higher temperatures and radiates heat more effectively. On top of that, Starship's metallic shield would be much thinner than P170 and wouldn't need to be cooled all the way down to room temperature during re-entry. So, while DLR's results offer a useful starting point, they can't be applied directly to Starship. To truly understand how a stainless steel, water-cooled heat shield might perform, dedicated experiments will be needed. Still, the DLR numbers give us at least a baseline, a rough, worst-case scenario, for estimating how much coolant Starship might require. If we assume Starship's water-cooled heat shield were to cover an area equal to half a cylinder, roughly 800 square meters or 8,600 square feet, then actively cooling the entire surface under extreme conditions would demand about 52 kilograms of water per second. Of course, this is a massive oversimplification. In reality, heat during atmospheric reentry doesn't spread evenly across a spacecraft's surface. Aerodynamics create complex airflow patterns that concentrate thermal loads in certain regions, like the leading edges and control surfaces. These hot spots require specialized thermal protection systems, TPS, capable of withstanding far more intense conditions. For example, NASA's Space Shuttle relied on fragile reinforced carbon-carbon tiles on its leading edges. DLR, on the other hand, explored water cooling as a safer and potentially more reliable alternative in its theoretical spaceliner concept. Starship's design could take a similar approach, using targeted active cooling on critical sections, while applying less resource-intensive methods to the rest of the surface. That strategy alone would dramatically reduce the total water required during re-entry. Beyond just heat flux, the real unknown is when and for how long such a system would need to supply coolant. In a worst-case scenario, Starship might need to continuously pump 50-plus kilograms per second of water throughout the entire high-drag, high-heating re-entry phase, which could last over 5 minutes, 600-plus seconds. If the spacecraft also needs to rely heavily on aerodynamic braking to conserve propellant for interplanetary missions, it might require multiple cooling cycles per re-entry. That could add up to at least 15 metric tons of water per re-entry. The problem is obvious. While SpaceX envisions Starship delivering 100-plus tons of payload to the Martian surface, carrying 15 tons of coolant would eat heavily into that capacity. For deep space or interplanetary operations, that trade-off could make water-cooled shields impractical, at least in their most demanding form. Elon Musk once explained it simply. Basically, you just need a stainless steel sandwich. You run fuel or water between the layers of the sandwich, then you have tiny perforations on the windward side and essentially pump coolant through them to keep the rocket's leading surface cool. Although Starship's progress has been on track, even Elon Musk admits the challenge is far tougher than he ever imagined, simply because no one has ever pulled it off before. As he put it,
So no one has ever developed a truly reusable orbital heat shield. So that it's extremely difficult to do so.
And that's the core problem. It all comes down to the heat shield. In simple terms, the heat shield is the key to making a rocket reusable. Take Starship, for example. SpaceX wants it to safely re-enter Earth's atmosphere after every mission. But that's insanely hard. When a rocket comes back at orbital speed, it's carrying an enormous amount of kinetic energy. And that energy doesn't just scale with speed, it scales with the square of the speed, which means even a tiny increase in velocity leads to a massive increase in heat. That energy turns into extreme temperatures, heating the surface to thousands of degrees Celsius, hot enough to glow white. To survive, Starship needs a rock-solid thermal protection system made of individual heat shield tiles. The bigger the rocket, the more tiles you need, and the more weak points you create. And here's the real kicker. It's not just about surviving one re-entry. Musk wants a heat shield that can work again and again. On top of that, a reusable Starship has to save extra fuel for landing. It also needs 4 giant flaps to steer the ship through the atmosphere, all working in sync before it touches down on Mechazilla's arms. Every one of those systems adds weight and complexity. That's what makes this such a brutal challenge. So, stripping off that entire heat shield isn't necessarily a bad thing if Starship is only meant to fly once and carry priceless cargo into orbit. We're talking about missions worth billions of dollars, like the James Webb Space Telescope, which cost over $10 billion, or even Hubble. Coincidentally, astronomers have suggested that Starship's 9-meter fairing could carry telescopes even larger than JWST's 6.5-meter mirror without the need for those complicated folding designs. That alone could save years of development and billions in costs. And when a single mission is worth tens of billions, the profit margin easily covers the upper stage production cost, even if it's expendable. Without those 18,000 fragile heat shield tiles, a Starship upper stage might cost only $30 to $40 million to build. That's a bargain. In fact, Elon Musk himself hinted at this idea back in 2021 when he tweeted, "Over time, we might get orbital payload up to approximately 150 tons with full reusability. If Starship then launched as an expendable, payload would be approximately 250 tons. What isn't obvious from this chart is that Starship Super Heavy is much denser than Saturn V. Well, an expendable Starship would really just be a stripped-down version of the vehicle we know today. No heat shield tiles because it's not coming back. It flies once, burns through all its fuel, and puts the payload into orbit. The 4 giant flaps for reentry? Gone. At that point, it's basically just a massive flying steel stick. And that stripped-down design changes the numbers in a big way. Since it doesn't need to hold back hundreds of tons of methane and oxygen for landing, all of that propellant goes straight to orbit. That pushes the payload up to about 250 tons, and maybe close to 300 once Raptor 3 engines are fully in play. To put that into perspective, the entire International Space Station has a mass of about 420 tons. So, with an expendable Starship, you could match that with just 2 or 3 launches. That's insane. Of course, volume is another story, but you get the idea. In this configuration, the payload bay would look different too. No Starlink dispenser inside. Launching satellites on a one-off expendable Starship would be a complete waste. For that, Falcon 9 is still the better choice. On top of that, the vehicle itself would be a lot simpler and lighter. Right now, Starship's dry mass is around 100 tons, but take away the heat shield, the flaps, the landing gear, sensors, and all the Mechazilla hardware, and you could be looking at just 70 to 80 tons. At that weight, the Raptor engines would have a much easier job pushing the vehicle to orbital velocity, about 28,000 kilometers per hour, while burning less fuel in the process. And it's not just Starship that benefits. A lighter upper stage also takes some pressure off its booster, Super Heavy. Even if the upper stage is expendable, pairing it with a reusable Super Heavy still brings huge advantages. Reusing only the booster already recovers around 85% of the hardware, most of the cost, while adding only about 20% of the complexity compared to making Starship itself reusable. Oh, and here's another option. Orbital refueling is still on the table. You could imagine expendable tankers topping off a Starship in orbit, which would cut down the number of launches needed from maybe 4 or 5 to just a couple, for a mission to the Moon or even Mars. Sure, this approach would be more expensive than full reusability, but it could serve as a very practical stepping stone. Because even in expendable form, Starship would still be the highest capacity launch vehicle on the planet, unlocking mission profiles no other rocket could even attempt. Speaking of which, the Starship HLS variant, the one NASA is funding to the tune of about $4 billion, won't be equipped with heat shield tiles either. That's why, in the near future, maybe around 2026, we could see an expendable Starship built purely as a test vehicle to gather critical data for upgrading HLS ahead of its first crewed mission in 2027. Here's how that works. Once launched to low Earth orbit by Super Heavy, HLS would be refueled on orbit, then head out to the Moon's NRHO, near rectilinear halo orbit, before descending to the lunar surface. Since the Moon has no atmosphere, landing and lifting off won't generate the extreme heating you'd see during Earth re-entry. After completing its mission, HLS would return to lunar orbit to rendezvous with Orion or another NASA module. The astronauts would transfer back to Orion for the trip home, while HLS could either be reused for future lunar missions or left in lunar orbit. And because it never comes back through Earth's atmosphere, a heat shield simply isn't necessary. So, with all those advantages in mind, the question becomes, why is SpaceX, and Elon Musk in particular, still so determined to make Starship fully reusable? The simple answer is this. Starship's most immediate mission is Starlink, and that absolutely requires reusability. At the Barron Investment Conference in November 2024, Gwynne Shotwell put it bluntly. Starship obsoletes Falcon 9 and the Dragon capsule. She predicted that SpaceX would keep flying Falcon 9 and Dragon for another 6 to 8 years, so roughly until 2030 to 2032 after the ISS is retired. But eventually, all of Falcon 9's missions, including satellite launches, will move over to Starship. And here's the key point. If Starship were expendable, SpaceX simply couldn't build enough rockets to keep up with Starlink's launch demands. Throwing away a brand new Starship every time just isn't sustainable, either in terms of production capacity or cost. In reusable configuration, Starship can carry 10 times the payload of Falcon 9, around 150 to 200 tons, and do it at a staggering price drop. Roughly $100 per kilogram to orbit, compared to the $3,000 per kilogram that NASA is used to paying. That's the kind of leap that doesn't just impress, it shocks the entire industry. But that doesn't mean an expendable Starship has no role to play at satellite missions. In fact, there are some scenarios where a one-off launch could still make a lot of sense. One obvious use case is giant rideshare missions. Just like SpaceX already does with Falcon 9, a third party could gather 50 to 100 small satellite customers into one launch. Even Amazon, Jeff Bezos' company, has to buy launches from SpaceX for its Kuiper internet constellation. All of these customers want the same thing: safe, reliable access to orbit at the lowest possible price. A one-off Starship launch could deliver exactly that, especially to popular destinations like Sun's synchronous orbit. Or take this idea. NASA could buy a single expendable Starship, fill it wall-to-wall with low-cost science hardware, and send it on a deep space mission. No need for ultralight, radiation-hardened cameras. Just pack in 1,000 off-the-shelf instruments, and then invite universities, ESA, JAXA, and other agencies to join. Everyone shares the cost, everyone shares the glory. That kind of low-cost, high-mass platform could open up exploration of places like Venus or Jupiter in ways that simply haven't been possible before. Looking ahead, if SpaceX really does set up an outpost on the Moon, or even Mars, they're going to need to move massive amounts of gear, construction materials, and life support systems down to the surface. And for that kind of mission, an expendable Starship is almost indispensable. A basic lunar outpost would need all sorts of heavy hardware, living modules, power systems, from solar arrays to small nuclear reactors, rovers, ISRU equipment, and even building materials like regolith-based concrete. Put together, that easily adds up to hundreds of tons. This is where Starship's payload capacity truly shines. After refueling in orbit, a one-off Starship could deliver 100 to 150 tons straight to the lunar surface in a single flight, enough to set up most of an outpost's core infrastructure in just one or a handful of launches. Compare that to NASA's SLS Block 1, which can only push about 27 tons to lunar orbit TLI. And the real kicker, cost. With an estimated $100 to $150 million per launch, an expendable Starship is drastically cheaper than SLS, which sits at roughly $2 billion a shot. That kind of price difference could let NASA or private partners run far more missions, even with the tighter budgets that are almost certain in the years ahead. But going expendable also means Starship would have to give up another potential role, serving as a rapid Earth-to-Earth transport system. The point-to-point concept was first introduced back when Elon Musk unveiled Starship under its original name, BFR. The idea was to repurpose rockets designed for orbital or suborbital flights to move cargo, or even passengers, across the globe in a fraction of the time it takes conventional aircraft. That opens up a market far bigger than traditional satellite launches. SpaceX President Gwynne Shotwell has emphasized this capability, noting that Starship could operate much like an airplane, take off from one part of the Earth and land on the other side in just 30 to 40 minutes. The longest part of such a trip, she pointed out, wouldn't be the flight itself, but the commute to and from offshore launch pads. Imagine it, a flight from New York or Vancouver to the opposite side of the planet in under an hour, cutting travel times by an order of magnitude compared to commercial aviation. Just a few days ago, observers spotted a rare scene inside the Star Factory. All 3 generations of the Raptor engine, versions 1, 2, and 3, lined up neatly side by side. That arrangement is almost certainly intentional, as Elon Musk has hinted at a major technical update on Starship, with Raptor 3 likely to take center stage. The most striking detail in the photo is the Raptor SN20. At first glance, it might look no different from the earlier engines, but with the sharp eyes of engineers, it becomes clear that SN20 carries some significant upgrades compared to the SN1 prototype, unveiled back in August last year. To really see what I mean, let's take a look at this photo. Alright, so as you can see, I'm not exactly sure which SN version these upgrades started on, but on SN20 there are 3 noticeable changes. First, right at the Methalox feedline joint, they added a gray collar that basically acts like a protective buffer, shielding the joint from the insane vibrations of Raptor 3, which can push out up to 280 tons of thrust, thanks to the full flow stage combustion cycle. Just to the left of that collar, you can also spot that SpaceX wrapped the methane turbopump area in a metal casing, probably to tidy things up and give the engine a cleaner, more robust look. Oh, and I almost forgot. SN20 also comes with a Texas flag, which is pretty interesting. Imagine if Gavin Newsom had been a bit nicer to SpaceX. Maybe it would be flying around with a California flag instead. Then there's the third upgrade over at the hot gas manifold part. Elon Musk mentioned there was a technical issue with the Raptor 3 at the connection between the thrust chamber and the manifold. Originally, this joint used a bolted flange, which he described as ugly, unreliable, and heavy. The problem was that it added extra weight, could loosen under extreme heat and pressure, and made manufacturing more complex. SpaceX's solution was to switch to a welded joint, which cuts weight. Raptor 3 now comes in at just 1,525 kilograms, makes the connection stronger and leak-proof, and even improves gas flow inside the engine. Of course, welding introduces its own challenges, like being harder to maintain and requiring super precise techniques, especially when you're joining different metals like copper alloys for the chamber and Inconel for the manifold. To deal with that, they added a protective plate over the weld, keeping it safe while the engine stays reliable. It seems these upgrades actually stem from a Raptor 3 explosion during testing at SpaceX's McGregor facility in Texas back in May. The blast was sudden, sending flames shooting up, but luckily it was quickly contained. The root cause hasn't been officially revealed, but it looks like they were intentionally pushing Raptor 3's thrust up toward 300 tons, which put massive stress on the engine structure. So, yeah, that McGregor incident might have been part of the plan. They were simulating conditions the engine might face in space, violent vibrations, turbulent flow, to see how every tiny component, inside and out, holds up. According to a reliable source, SpaceX has been ramping up engine tests at McGregor since early August, running 24 engine burns in a single week, covering both Raptor 2 and Raptor 3. One major milestone included a 201-second burn on the Raptor South test stand, the longest Raptor 3 burn recorded at that time. But it's also possible that the incident happened because they intentionally messed with the mixture ratio of liquid methane and liquid oxygen to see what would happen. Wait, just getting the mix wrong can actually make it explode? As Elon Musk said, very complex startup sequence. Insane timing precision is needed to avoid blowing up the engine. To understand why Elon Musk said that, let me break it down. Raptor 3 is an advanced rocket engine that runs on liquid methane and liquid oxygen using a full-flow stage combustion cycle. That means the fuel and oxygen go through 2 separate pre-burners before reaching the main combustion chamber, where they combine to produce massive thrust. The methane to oxygen ratio has to be insanely precise, like brewing a perfect cup of coffee with the exact water to coffee balance. Get it wrong, and everything goes haywire. Think of Raptor 3 like a superpowered gas stove, but instead of a tiny flame, it's producing a fireball with pressures up to 350 bar. Inside, methane and oxygen are pumped into 2 pre-burners, one mostly methane with a little oxygen, and the other mostly oxygen with a bit of methane. The hot gases from these pre-burners then pass through the hot gas manifold before mixing in the main combustion chamber to burn completely, generating the thrust that launches the rocket. If the mix is off, too much oxygen or too little methane, the burn becomes unstable. Too much oxygen can overheat the metal, melting parts of the combustion chamber or other components. Too much methane can cause incomplete combustion, leaving residue or even triggering small explosions as excess fuel suddenly ignites. It gets even trickier because Raptor 3 operates at extreme pressures and speeds, so everything has to be perfectly synchronized, down to fractions of a millisecond. If the ratio is off, the pressure in the chamber can oscillate violently, like waves sloshing back and forth in a pool. These combustion oscillations can shake the engine so hard that parts like the hot gas manifold or fuel pump turbines crack or fail. In the worst-case scenario, a sudden pressure spike, like overinflating a balloon, can make the whole engine explode. This is called a hard start, a dangerous event when the fuel mixture ignites too quickly or at the wrong moment. But thanks to the May incident and the latest upgrades they have revealed, it looks like in the future, issues like this could be much easier to prevent and fix. So, the big question now is, when are we actually going to see Raptor 3 fly? Well, to answer that, we'll probably have to wait for Elon Musk's technical update livestream. The original plan was for him to share it on Sunday, but now it's been delayed. No worries though, this was totally predictable. As we all know, Raptor 3 is only equipped on Starship Block 3 and beyond. Flights 10 and 11 are still using Starship Block 2, so if Flight 11 happens sometime in September, we could see a version 3 Starship as early as October or early November this year. And there's good reason to think so. Just 2 weeks ago, cameras at Starbase caught Ship 39's nose cone being mounted onto the payload bay section, and Ship 39 is set to be the first of the version 3 Starships. From now until October, there's plenty of time to finish assembling the ship's structure. But what about the engines? Do they even have enough Raptor 3s ready to install? Right now, probably not yet, because on August 13th, someone spotted Raptor 3SN29 at McGregor, which means they currently only have around 30 engines that have been tested and could be ready for use. A complete Starship needs 39 Raptor 3s, 6 for the upper stage and 33 for the Super Heavy booster. But by October, they should definitely have enough engines to assemble a full Block 3 vehicle, and November could be the perfect time to see them roaring across the sky for the first time. Still, SpaceX can't get too comfortable. A German company just announced that they've completed a 6-week test campaign on their full-flow stage combustion rocket engine, the same technology SpaceX uses with Raptor. Named Typhoon, the engine's oxygen-rich pre-burner was tested at the Lampoldshausen site of the German Aerospace Center DLR. The propulsion system underwent 16 hot fire tests. This reusable engine has been in development since 2024, with co-funding from the French space agency CNES. Designed to produce 250 tons of thrust, it uses the full-flow stage combustion cycle. The company revealed that these 16 hot fire tests were conducted across 4 different configurations, covering a wide operating range. Early low-frequency instabilities were resolved, allowing for stable firing sequences of up to 85 seconds by the end of the campaign. The pre-burner powers the engine's turbines, pumping fuel and oxidizer into the combustion chamber at high pressure. Once the engine overcame the initial instabilities, it achieved stable burns for up to 85 seconds, a significant improvement over earlier tests conducted earlier this year. Exploration Company has reached another important milestone. We're excited to contribute our expertise to the development of future space propulsion systems and appreciate the trust and effective cooperation, the DLR Institute of Space Propulsion said in a social media post. According to the company, this reusable engine uses a full-flow stage combustion cycle and is designed to produce 250 tons of thrust, even 20 tons more than Raptor 2. Right now, the Typhoon engine hasn't been confirmed for use on any rocket because the company believes it's too powerful for any current space logistics project. Exploration Company has teamed up with a major industrial partner to submit a proposal for the European Space Agency's European Launch Challenge. While it's not official yet, according to European Spaceflight, the company's contribution could include the Typhoon engine. And once it's in action, possibly as soon as 2026, it could directly challenge SpaceX's engine production. That's why the ultimate counter is Raptor 3. There's no other engine out there that can beat Typhoon, so let's cheer on SpaceX by dropping a 1 in the comments. Now, let's move on to another bit of SpaceX news. They just completed their 33rd cargo delivery to the International Space Station early Monday morning as a Dragon supply ship smoothly docked with over 5,000 pounds of science experiments and essential supplies for the 7-person crew aboard the lab. This resupply flight is part of the regular rotation of cargo and crew missions that keep the station running. But this time, there's a little twist. Instead of just the usual pre-packaged space food, the Dragon carried fresh food, including around 1,500 tortillas, along with equipment for several experiments. These include testing 3D printing in microgravity and studying how the human body responds to long-duration spaceflight. Although this was SpaceX's 33rd cargo delivery mission to the ISS under NASA's multi-billion-dollar commercial resupply services contract, it also marked a much bigger milestone. the 50th Dragon mission to the station overall. And that number includes 17 Crew Dragon flights carrying astronauts. What's even more interesting about this flight is that it ties into some important work on the ISS. Normally, SpaceX's Dragon cargo ships dock at the forward end of the station's main axis, which theoretically makes it easier to adjust the station's orbit. But of course, SpaceX has to make sure Dragon has enough fuel to reach the ISS and return safely to Earth. Its 16 Draco thrusters aren't fully maneuverable. Yet last year, SpaceX proved they could perform small orbital adjustments for the station. The station's altitude gradually decreases over time due to drag from the thin atmosphere at our orbit, said Bill Spetch, NASA's director of ISS Operations Integration. To counteract that drag, we occasionally need to boost the station's altitude. In the past, the Russian Space Agency handled most of the station's orbital maintenance. After NASA retired the Space Shuttle in 2011, Progress cargo ships were the only vehicles capable of reboosting the ISS. They could also refuel the Russian segment, letting the station perform maneuvers independently when needed. Congratulations to SpaceX. To achieve great results and gather valuable data from Starship Flight 10, they had to push constantly, making sure the flight stayed on schedule and hitting near-perfect precision, all thanks to the insanely talented engineers and specialists Elon Musk brought together. Looking back from Flight 9 to Flight 10, it definitely wasn't an easy ride. The flight was originally scheduled for late June, but the explosion of Ship 36 at Massey site caused a long delay, almost 2 months. During that waiting period, SpaceX worked tirelessly to repair the test area at Massey site, spending tens of millions of dollars just to restore it. At the same time, their engineers held meetings to plan modifications to the BQD on OLM Pad 1 so it could properly connect with the upper stage of Starship and perform a static fire. And the wait felt like a whole year. Flight 10, originally set for August 24th, was delayed the first time due to ground system issues. Then it moved to August 25th, but the weather was terrible, with massive electric clouds forcing another pause. It wasn't until the third attempt that they finally launched successfully, just like the saying goes, third time's the charm. In the end, it was exciting to see Ship 37 take over and flawlessly complete all the missions of Ship 36. But while everyone was focused on the vehicle and its recent achievements, the launch pad itself, a system often overlooked, faced serious issues. There wasn't much time to celebrate, as SpaceX engineers had to sit down and figure out a solution for the badly damaged BQD on the OLM. To really understand the severity of the situation, take a look at this video. Do you see that? Just seconds after ignition, all 33 Raptor engines on Booster 16 roared to life, lifting the booster into the sky. Thick steam from the water deluge system erupted to protect the launch pad, but the raw power of the booster was overwhelming. At full thrust, the engines produced nearly 7,600 tons of force, and combustion temperatures reached 2,500 degrees Celsius, about 4,500 degrees Fahrenheit. The BQD began retracting its connection arms, and the hood closed to shield itself from the intense heat. But that was pointless. Just seconds later, the searing flames struck the BQD directly, causing severe burning so intense that it glowed white hot. With damage this extreme, the fuel lines inside were likely destroyed, and the thin metal hood couldn't protect the internal systems. The QD system was scorched, not just on the surface, but deep inside, with some areas showing cracks and partially melted edges. If a robust system like the QD could be this badly damaged, it's safe to assume that thinner fuel lines and smaller ground connections farther away were likely affected as well. Now, with the visible damage, SpaceX may need major reinforcements, or even complete replacement of some components. Naturally, this will impact the next flight, since the launch pad is responsible for a crucial step, the booster static fire test. Without a fully functional QD system, this test simply can't happen. That brings us to the big question. For Flight 11, which vehicle will perform the static fire at the OLM once the BQD is repaired? Based on the information we've gathered, there are currently 2 boosters likely to take part in Flight 11. First is Booster 15, which landed successfully and was caught by Mechazilla during Flight 8. The second is Booster 17, a brand new stage. However, for the next flight, Booster 15 seems more likely. In Flight 10, SpaceX collected valuable data on pushing the vehicle to its limits using high attack angles with Booster 16. This data will help them optimize fuel for landing, so they probably won't repeat the same extreme test. Booster 15 is a previously flown rocket, just like Booster 14 was reused in Flight 9 to test a booster, and the data collected then helped maximize its reusability potential. Booster 17, on the other hand, has been sitting in the rocket garden untouched for over 4 months. There's also word that it was being kept as a backup in case Booster 16 had to divert during Flight 10. So, which booster do you think will fly, B-15 or B-17? Comment your answer below, and let's see who gets it right. Personally, I'd go with Bravo 15, paired with Ship 38 for this mission. Speaking of Ship 38, SpaceX seems to be moving quite fast with preparations. On August 27th, cameras at Starbase captured a crane delivering one of the aft flaps into Mega Bay 2, and the very next day, the remaining flap was brought in as well. As for the Raptor engines, Ship 38 had them installed in mid-August, meaning the only major steps left are attaching the 2 forward flaps and finishing the heat shield. Well, it looks like they'll still conduct not only the cryo test, but also the static fire for Ship 38 at the launch pad, because Massey Site hasn't just been repaired, it's been significantly upgraded. On August 6th, observers spotted the Starship static fire stand still being reinforced with steel beams around the new stand, with replacement pipework for the flame deflector staged nearby, clearly indicating damage to the old deflector. At the same time, they've begun shifting booster static fire operations over to Massey. That means, in the future, booster static fires may no longer be carried out at the launch pad. Instead, the site is being optimized for version 3 vehicles. Here's an example. On August 21st, they completed installation of the new booster quick disconnect for version 3. Looks pretty simple, doesn't it? That also means SpaceX will once again have to go through the complicated process of removing the booster clamps at OLM Pad 1, then installing and reinforcing the ring wall stand, a sort of stool that allows Ship 38 to sit securely on top. After that, they'll need to stabilize it properly before running the vehicle's test campaign. But this will almost certainly take place only after Booster 15 completes its static fire. Since B-15 is a reused vehicle, they won't be running just a light check this time. As for the mission itself, if Booster 15 proves to be in good condition, SpaceX will attempt a dramatic Mechazilla catch, showing that the booster isn't just capable of flying once, but multiple times. That would be a powerful demonstration of the company's original goal: rockets that are fast, affordable, and safe to reuse. So, what about Ship 38's mission? Will it be caught by the tower this time? The answer is no. After Starship Flight 10, Elon Musk made it clear. Starship catch is probably Flight 13 to 15, depending on how well version 3 flights go. The Starship flown in Flight 10 was a version 2, which shares the same size as the upcoming version 3 rockets, but with lower payload capacity and weaker thrust from both the ship and its booster. Musk noted that only one more V2 will fly before the transition. Starting next year, V3 will be the workhorse through 2026, while V4, SpaceX's most capable design yet, may well be the first Starship to carry humans to orbit. Musk also mentioned that SpaceX hopes to attempt the first Starship catch in 2025. But realistically, this timeline may slip into 2026 due to scheduling constraints. To stay on track, SpaceX will need to get through Flight 11 soon, Flight 12 by the end of the year, and only then move toward Musk's projected Flight 13 catch attempt. It wouldn't be unprecedented, but with only 3 test flights completed this year, the company will have to accelerate its launch cadence significantly. And if SpaceX's pace remains this slow, government intervention may eventually come into play. Why? Because Washington has shown increasing interest in taking ownership stakes in defense contractors. Every year, the U.S. government spends hundreds of billions on defense companies. Yet, during Trump's administration, officials hinted they wanted more than just goods and services. They wanted ownership or equity. In an interview, Commerce Secretary Howard Lutnick revealed that the Pentagon was considering equity stakes in defense suppliers. He argued that current funding for munitions procurement had been too frugal and needed to be rethought. The idea, floated at the same time the government was weighing a potential stake in Intel, shocked many analysts. Big defense primes are strong enough to push back against such demands. But for a fast-growing private company like SpaceX, tighter government oversight could prove especially contentious, something Elon Musk would resist fiercely. After all, Musk has publicly sparred with Trump himself just months ago. Unlike struggling players such as Intel or MP Materials, which sold equity for federal funding, SpaceX and the top defense primes are financially solid. Boeing, for example, raised $24 billion in equity last year alone. Back in June, as Musk's relationship with Trump soured, former White House advisor Steve Bannon even suggested using the Defense Production Act to take control of SpaceX. That's unlikely. The Supreme Court ruled in 1952 that nationalizing steel plants was unconstitutional, and seizure powers under the DPA were repealed in 2009. Besides, SpaceX dominates launch services and low Earth orbit satellites. The U.S. government has few alternatives for contracts worth some $13 billion, leaving Washington with little real leverage. As Kimberly Siverson-Burke of Quilty Space Consulting explained, Musk has no incentive to sell shares. He doesn't need cash, and he doesn't want outside oversight. Even a single external shareholder would change the dynamics entirely. Transparency, board seats, audits, that's Elon's worst nightmare, she said. The Pentagon declined to comment, but the White House noted it would continue seeking arrangements to ensure taxpayers benefit from federal investments. Historically, the government has taken equity stakes only to rescue companies in crisis, such as banks and GM during the Great Recession, or airlines during the pandemic. Trump's approach is different, targeting healthy companies. Recently, the administration demanded golden shares in U.S. Steel and purchased a 10% stake in Intel in exchange for funding. Analysts warn that forcing defense contractors into such deals could spark conflicts of interest, undermine investor confidence, and even chill venture capital in defense startups. Clearly, the road ahead for the Starship program is filled with challenges. Issues can arise from unexpected places, whether from politics or technical setbacks within the SpaceX itself. While such obstacles may slow progress, they also serve as an important reminder. Even in an era of rapid innovation, SpaceX must stay vigilant, methodical, and precise in addressing every problem. The QD failure is just one example, a single component in Starship's massive and complex launch system, yet it highlights a much broader truth. To succeed in the quest for space, SpaceX must continuously refine, improve, and adapt. It's a monumental task, but not an impossible one. Right now, all eyes are on how the company will overcome this first hurdle on the path to Flight 11. The repairs at Pad A will be the next test, not just of hardware, but of SpaceX's ability to maintain momentum in the face of setbacks. With determination, innovation, and relentless drive, SpaceX will keep pushing forward, one launch at a time. If you enjoyed this episode, don't forget to support us so we can bring you more updates like this. Thanks for watching. Yes, it looks like SpaceX has done it again, rewriting its own legendary history with Starship Flight 10. Just a few months ago, they faced 3 consecutive Starship failures on Flights 7, 8, and 9. Every launch seemed to bring a new technical problem, some so serious that $50 million vehicles literally blew up in midair, leaving engineers scrambling to fix the next one. But with Flight 10, all that hard work finally paid off. SpaceX didn't just conquer the challenges of building the largest, most complex spacecraft in the world, they also won the hearts of partners and fans alike. It's hard not to think back to Falcon 1's 3 early failures between 2006 and 2008, when the company was on the brink of bankruptcy. Elon Musk had to borrow money everywhere just to make a 4th attempt. Had that flight failed, we might never have seen SpaceX rise to where it is now, and Musk probably wouldn't be the richest person in the world. Instead, success came. That breakthrough led to a $1.6 billion NASA contract for ISS resupply missions, a foundation for the SpaceX we know today. With Flight 10 behind us, all eyes are now on Flight 11. We are hoping for another success, maybe even bigger, since this will be the final Starship Block 2. Every mission it carries could bring surprises we haven't seen before. But before we go any further, everyone's asking the same thing: when is the next launch? Back when the Massey site was operational, SpaceX would perform static fires for the Starship upper stage there, while the Super Heavy booster was tested at the launch pad. This setup allowed for a much faster schedule, with a new flight potentially ready just 4 to 5 weeks after the previous one, if no issues arose. Now, with Massey Site being upgraded for Starship version 3, all testing for both stages is done at OLM Pad 1. Upper stage tests also require modifications to the OLM, a process that can take a full week just to disassemble and reassemble. Because of this, Flight 11 is likely 1.5 to 2 months away, which puts the launch in the latter half of October. This pace is both practical and strategic. A launch in October keeps the schedule steady without rushing, increasing the chances of success, just like Flight 10, which had nearly 3 months of prep time. All of this also sets the stage for Flight 12, the first of the version 3 Starships expected in December. That milestone won't just maintain momentum, it'll satisfy the anticipation of everyone eager to see the next generation of Starship take flight. However, while that may be Musk's broad estimate, the current pace suggests Flight 11 could actually happen sooner, maybe in early October. Let's take a closer look at the progress so far. Ship 38 has already completed its cryogenic testing, and Booster 17 has also passed cryo tests. But interestingly, Booster 15 seems like a stronger candidate. It was previously used on Flight 8, and could very well be assigned to this mission. Either way, the hardware is clearly moving in the right direction. At this stage, the only major step left is a static fire before moving on. B-15 still has its engines, though a few might need replacement. It's currently stored inside Megabay 1, while B-17, despite reportedly having its full set of engines, has been sitting in the rocket garden for months without much activity. Meanwhile, engines have been delivered to Megabay 2, where preparations for Ship 38 are making steady progress. As of the morning of August 27th, Ship 38 had even received its second aft flap, a key milestone that shows it's nearly ready for the next round of testing. All signs suggest the hardware itself is getting close to flight readiness. But there's another critical factor: the launch pad. Flight 10 was a powerful high-stress test, and the orbital launch pad took a heavy beating. Systems like the booster, quick disconnect, and the ship quick disconnect appear to have been impacted by the sheer force of the engines blasting directly onto them. Repairs are already underway and are expected to take about another week. In the meantime, SpaceX has also been testing the chopsticks, lifting, lowering, and catching motions, to make sure everything is fully operational again. Once the refurbishment is complete, Booster 15 will likely be rolled out to the launch pad for a new static fire test. After that, it'll head back to the production site for a full inspection and the installation of its hot staging ring. At the same time, the ship's test stand and the modified ship quick disconnect will be reattached to the orbital pad, paving the way for static fire tests of Ship 38. Just like previous campaigns, the ship could go through 2 rounds of static fire before moving forward. If everything goes smoothly, Ship 38 will then return to Megabay 2 for final checkouts, payload installation, and flight safety system integration. All these steps point to a timeline of about 1 month. At this pace, it's not impossible that Flight 11 could launch as early as the beginning of October. And just like Musk said after Starship Flight 9, launch cadence for the next 3 flights will be faster, at approximately 1 every 3 to 4 weeks. That would mean back-to-back launches, something SpaceX has proven it can handle and might have already achieved with Flight 10 if not for the Ship 36 delay. Still, it may be wise to temper expectations. After all, Flight 10 was a major milestone that took months of preparation. It wouldn't be surprising if SpaceX took a slightly more cautious approach this time, making sure every detail is perfect before committing to the next launch. For that reason, mid-October feels like a more realistic target, a balance between speed and reliability. Personally, though, I'm betting on October 24th, since SpaceX often favors launches in the final week of the month. What about you? When do you think Flight 11 will launch? Drop your guesses in the comments. Let's see who gets it right. It's not just the launch date that's drawing attention. The objectives for Flight 11 are just as ambitious. After the success of Flight 10, many expect SpaceX to raise the bar even higher. The company has already shown that Starship can advance rapidly, and now it seems ready to push the limits further. For the Super Heavy booster, one key area will be reusability. By flying Booster 15 again, SpaceX will likely continue testing high-angle reentry profiles to refine landing techniques. And, if conditions allow, meaning the booster isn't too damaged during descent, a full catch with Mechazilla could finally be on the table. So far, SpaceX hasn't nailed a successful landing in a true reusability configuration. On Flight 9, for example, Booster 14 was reused but failed during re-entry. The steep angle and stress on internal fuel lines caused a structural break in fuel mix, leading to an explosion. This time, though, SpaceX may go all in, aiming to land B-15 with Mechazilla. If they succeed, it would be a huge leap toward making Starship fully reusable. But before any of that, there's still one critical issue: engine reliability. In Flight 10, one of the center engines shut down completely right after liftoff. The booster still carried on, but every loss of thrust adds unnecessary risk, and SpaceX will need to fix that moving forward. Even more concerning was the unexpected explosion in the engine bay later in the mission. The root cause hasn't been officially confirmed, but many believe it may have been linked to something as simple as the engine's cooling system. During flight, propellants that vaporize inside the lines must be vented to prevent dangerous pressure and temperature buildups. Starship has 2 vent ports at the base of its aft flaps, one for liquid oxygen and one for methane. A crack in one of these Raptor chill-down lines, likely the LOX vent, may have created the initial leak, damaging the flap in the process. After that, a large amount of gas appeared to vent from the methane port. With the outlet path possibly blocked, pressure built up, then suddenly burst out in a jet of gas. Moments later, a bright flash erupted. Then, boom! The explosion ripped through Starship's skirt, scattering debris. The most likely scenario is that methane and oxygen from both vents mixed together and ignited when exposed to the extreme plasma environment of re-entry. The deeper reason is that SpaceX has been pushing Starship right to its limits by deliberately removing some heat shield tiles near the windward side to expose insulation. They allowed plasma to burn into vulnerable areas around the aft flaps. That damage may have compromised the venting system, triggering the chain of events that led to the blast. This minor incident also gives us a clear hint. If SpaceX wants to push Starship even further, the vehicle will need to be fully equipped with ceramic heat shield tiles. Only then can it survive re-entry from true orbital altitudes without risking another explosion. With proper protection in place, the ship could safely make it back through Earth's atmosphere, and a controlled splashdown in the ocean would be the expected outcome. Alongside these upgrades, SpaceX will also look to build on the successes from Flight 10. The controlled flip maneuver and the 2-engine landing burn are expected to be repeated, giving the team more confidence in these critical procedures. Another key focus is the final landing of Super Heavy. In Flight 10, the booster hit the water too hard and was destroyed. This time, engineers may fine-tune the landing sequence to achieve a gentler, more controlled splashdown, with the ultimate goal of keeping the booster intact long enough to gather more post-flight data. As for Starship itself, specifically Ship 38, the mission begins with liftoff. While Flight 10 finally marked a clean ascent to space, the 3 flights before it were plagued with major issues. SpaceX will certainly want to prove that those failures are behind them. Consistency during ascent is going to be a big part of showing Starship can be trusted. Once in orbit, the next challenge is payload deployment. Flight 10 demonstrated an early version of this by releasing 8 dummy Starlink satellites on a suborbital trajectory. For Flight 11, expectations are much higher. Many believe Starship could carry twice as many, up to 20 satellites, this time simulating Starlink version 3 units, which would total around 40 tons. And instead of a suborbital release, they might actually deploy them from a real orbit. Since this is the last mission of the Starship version 2 design, SpaceX may well attempt some bold, unpredictable steps. Moves like this bring the vehicle closer to its real purpose, delivering satellites, cargo, and eventually humans to orbit. And you know what? SpaceX's victory with Starship Flight 10 ended up being a pretty embarrassing moment for Blue Origin. Their original plan was to launch the company's reusable New Shepard rocket on August 23rd, carrying a batch of suborbital science experiments from Launch Site 1 in West Texas, just one day before SpaceX's big flight. But suddenly, Blue Origin announced a delay. On social media, they wrote, "We are scrubbing today's NS-35 launch. The team encountered an issue related to the booster's avionics. New launch target forthcoming." At first, it almost looked like a PR move, like they didn't want to risk being overshadowed by Starship's headlines. If New Shepard had flown successfully right before Flight 10, Bezos's company could have stolen a slice of the spotlight. That kind of timing game is a classic PR trick in competition. But when August 26th came around, Blue Origin had to push it back again, saying, "We're standing down on today's NS-35 launch attempt to continue to troubleshoot an issue with the booster's avionics. We're determining the next launch opportunity." And just like that, the plan collapsed. Once again, Blue Origin fell behind while SpaceX surged ahead. It's also hard not to see this as part of the ongoing billionaire rivalry. Years ago, Jeff Bezos was the big name everywhere, while Elon Musk was just the eccentric engineer obsessed with code and rockets. But success after success flipped the script, and today, Forbes doesn't even give Bezos a chance to